Clayton, take it away.
All right. Well, thanks to the organizers for inviting me. I'm glad to be here. So this is my talk on surface slices and homology spheres. This is a project I've thought about for a long time, but I'm glad I could finally kind of put it together. I first had this idea like 4 years ago, but let's get into it. So here's roughly the kind of structure of the talk. So first I'll have a little bit of an introduction about like I don't know, kind of the history of the problem, like not a ton, but partially why the specific result I have is of interest, and what the result is. Then I'm going to talk a little bit about the obstruction we'll be using. Oops, I don't know why that happens sometimes, but it does. Then I'll talk about the constructions that we'll be using, for that obstruction, because the construction is the obstruction is a little bit finicky. And then finally, I'll talk about how we'll be putting that all together into an actual proof. Okay, because again, the obstruction is a little finicky. All right, so first introduction. Okay, so really this starts with sort of one central question, which is sort of which three manifolds embed smoothly into S4. This is I think Kirby problem 3.20. I didn't check that. I just wrote that off the top of my head. I think that's right. It's a very open-ended question. In some sense, this is maybe the hardest Kirby problem because it would require you to like have a classification of three manifolds and then somehow apply some obstruction to all of those. And like, this might like answer, like the smooth Poincare conjecture is probably contained in this question because like, if there is such an obstruction, then probably there's some difference in embeddings of three manifolds. But regardless, it's you can still make progress on, certain small aspects of it without, proving this full, very open-ended question. Okay, so let's talk a little bit about some obstruction techniques. So the first one that I know of is this theorem by Hanscha. So this isn't quite in the form that he put it in. I think there's a more general form for a general three manifold because ones that can even have like B1. But here's the form for a rational homology sphere that I'm going to mention. So this is let Y be a rational homology sphere. If Y embeds in S4, then its first homology has to look like this double. So you get two copies of G for some group G. And that already sort of, narrows down the list of potential manifolds that embed smoothly into S4, or I mean, just embed at all. For example, you can't get lens spaces because, they don't have the right H1. All right, so there's a few ways that you can kind of soup up this in invariant. Well, I don't know, maybe I shouldn't say that it's quite souped up. It's just sort of a different obstruction technique, but I guess I see it as like, I don't know, there's like the same core thing. So one example is the D invariance. So what's going on here? So the D invariants are these kind of cobordism, homology cobordism obstructions. So, and in particular, if you have an embedding into S4, then the splitting that you'll be getting will give you kind of two, homology cobordisms to S3. And the idea is that something particular about their homology, which tells you something in particular about the spin C graded D invariance. And in particular, sort of, we already know, if we're following this obstruction, that it would have to be in the form, H1 would have to be in the form G plus G. So we know that, the D invariants are this G plus, are going to be this G plus G torsor. And in particular, a row and a column of them will have to vanish. And those kind of correspond to, these four manifolds that would be making up the splitting of S4. And one thing to note is I think this works for any like spin C graded homology cobordism group homomorphism in a similar way, if you have any of those other ones lying around. I think the first people to really use this that I know of at least are Andrew Donald and Ryan Budney and Benjamin Burton. Another nice obstruction to, let me get this out of the way. What's going on here? Okay, there we go. Another nice obstruction is using Donaldson's theorem. This one's a little bit, I'm not going to get into the details of this, but this one's a little bit more particular because, it requires certain definite four manifolds to exist, to bound, the manifolds that you're trying to obstruct. But in that case, you again kind of you want to attach one of these two four manifolds to that sort of a given definite four manifold to get a definite closed four manifold, and then using Donaldson's theorem, you want to use, the theory of lattice embeddings. But it's a little bit, again, like, because we're dealing with embeddings into S4 rather than just like obstructing certain co-boundings, there's some sense in which we need to understand how two manifolds sort of pair. So we're not just obstructing a single lattice embedding, but we're obstructing two simultaneous lattice embeddings that fit together nicely. Okay, so these are just kind of a few examples, but one thing that's kind of held in common with these examples is that all of these obstructive techniques are secretly obstructions to embedding in a integer homology S4, not in S4, right? The D invariants, you're only looking for, a homology cobordism group. You're only looking for a homology cobordism, so it's only really seeing that, you have a four manifold with the right homology information. Similarly, obviously, for this theorem, it's, homology itself doesn't really see the difference between a homology sphere and S4. And then Donaldson's theorem, it's the same idea. You really only are using the information that it's a homology sphere, not that it's S4. And so, this gives you a natural question, which is, are there three manifolds that embed in a homology S4, but not an S4, right? And, the answer, like, it's like, the answer is like almost definitely yes, right? Like before you even, really start thinking about this question hard. But, the question becomes, well, how do you actually find the proper obstruction? How do you find the proper construction, right? And so, again, my main theorem is going to be yes, there are infinitely many. And in particular, they don't even embed in any homotopy S4. So, for example, you can't use these manifolds to find a counterexample to the Poincare conjecture. Don't need to. I'm sure people were curious about that question. All right, so that's a little bit of an introduction. Let's talk now about some obstructions. Okay, so I guess here's a theorem of Tabs, which I guess there's some attribution to Akbulut. I've been told to say that, otherwise maybe I would get an angry email. So here's the theorem here. So let sigma be integer homology sphere that bounds a simply connected definite four manifold with non-standard intersection form. Again, that's kind of the most general way of saying it, but for our purposes, we're just going to think Poincare homology sphere. Well, I guess I didn't pause. Are people okay with things so far? It's always good to pause for questions. All right, so again, we have this manifold that bounds a non-standard definite four manifold. Then the manifold connects on its mirror, does not bound a definite simply connected four manifold. Okay, so how do we use this for we need a proper obstruction to embedding an actual S4, not in a homology S4. And what Andrew Donald noted is that we can use this above theorem to obstruct S4 embeddings. And so how can we do that? Well, here's the proposition. So let Y be a rational homology S3 such that there exists a definite simply connected cobordism W from Y to, this manifold we were just talking about. And then the conclusion is that Y does not embed in S4. Okay. So what's the idea here? Well, again, you take the splitting that you get of S4, and then you glue one of the pieces onto W here. And by Seifert-Van Kampen, we know that this, if we glue a submanifold of S4 in this way to W, then we're still going to get something simply connected because, of course, this is a splitting of, we know that, this is in a splitting of S4. So pi1 of Y normally generates kind of pi1 of this four manifold, which means that if we attach something simply connected to the boundary, then that should kill all of pi1. Okay. So in particular, this isn't actually this shows that this isn't actually an embedding obstruction to embedding in S4. It's an obstruction to embedding in a homotopy S4. And it actually turns out that, this ends up being a little bit too strong of a condition. Like this is kind of like the three manifold version of slice ribbon. So I think it's a bit hard to find manifolds that like don't satisfy this property via constructions. Like for example, my constructions like by definition won't work. Like you can't use branch covers.
I will ask
so we need, yeah.
Here you say rational homology sphere. The end periodic theorem version I know would require integer homology.
I mean, I think in this case, I think it shouldn't matter, right? Because like once you glue this to here, this should be, this doesn't have a boundary component that's a rational homology sphere. It just has the one closed that connects some sigma bar. Because remember, we said that sigma was
sigma is simply connected, or is a rational homology. Okay, got it.
It should be fine, I think.
Yeah.
Okay. In practice, the manifolds that I'll be using here will be integer homology spheres, but I think that this is how Andrew stated it. I guess it's the most general.
Yeah.
So wait, if you have a simply connected cobordism between the two, no, it could still be a rational homology sphere, not just an integer, because like you could just like have something like 3-framed or something. Okay. Other questions? Alrighty. All right, so we need to modify this construction a little bit. It turns out that this is like a nice idea, but like there's a few things we need to do to make
just to go back to that. I think you probably want to say not necessarily definite. Don't you want it to be somehow with an interesting intersection form, or
this non-standard intersection form?
Oh, okay. So it bound. Or sigma already bounds. Never mind. Okay, fine. I'm just not reading the full thing. Okay, go on.
Maybe I'm going through it a little quickly.
No, that's all right.
Okay. So we need to modify the construction a little bit here. So the first modification we'll make is that we're going to use work of Ali Daimi, which generalizes Taubes's work for a slightly stronger pi1 criterion, which will actually be super important to the end of our argument. And then there's also a slight generalization to the class of manifolds, or maybe not even slight. I don't work with these invariants super a ton, but here's the theorem. So this is not exactly how Ali stated it in his paper, but this is kind of the form that I'm going to be using, and it's very similar to Taubes's form. Like in fact, I just literally copy pasted this, but then I put in red the parts that are different. Okay, so let's read this. So what does it say? So it says, let sigma be, again, an integer homology sphere that bounds a simply connected definite form manifold with non-standard intersection form. He actually notes that you can just use something that has Froyschow H invariant non-zero. But again, we're just going to be using the Poincare sphere in this case, so that's not super important. Then sigma connects some sigma bar does not bound, instead of a simply connected definite form manifold, a definite form manifold such that pi1 admits a non-trivial SU2 representation that extends non-trivially to the boundary. And this SU2 representation is going to be important for the case analysis we'll do at the end. Though it's, to me, on the surface, it wouldn't be immediately obvious how to use that. It's sort of, it's clearly like a strictly stronger condition, but like, I don't know, SU2 representations. Okay, so the second modification to this construction will be that we're going to kind of relax the pi1 condition a little bit on the cobordism W. We don't actually need it to be simply connected. In fact, we don't even need it to like not admit a non-trivial SU2 representation. In fact, the example we'll be giving will admit a non-trivial SU2 representation, I believe. All we need to do is make sure that whatever pi1 condition we care about is satisfied once we actually glue, this rational homology ball to the cobordism. It doesn't actually need to be satisfied before that, right? And so this is maybe a little bit, this seems like a little bit vague right now. It'll be more specific once we get to the specific examples in question. Okay.
Sorry, can I just again add? I'm still confused. Mm-hmm. Isn't the point that pi1 of x shouldn't admit an SU2 represent? you're trying to generalize the condition that pi 1 of x is
Yeah,
trivial.
sorry. Yeah, so it does not bound a definite four manifold that admits.
Okay.
I mean, it's an abstraction. So again, it
No,
does
but
not bound a definite four manifold with these
No,
properties.
but sorry, sigma connects some sigma bar bound sigma cross I.
You mean punctured sigma cross? Well, that's not simply connected.
Right, but pi 1, but call that x. Pi 1 of x admits a non-trivial SU2 representation. I think you just want one more knot in there. So sigma connect. This is supposed to generalize saying that sigma connects some sigma bar doesn't bound a definite simply connected manifold, right? So you want to say pi 1 of x does not admit it. It doesn't bound a thing such that pi 1 of x does not admit. Am I missing something?
Sorry, wait. What?
Aren't you saying that it's a slightly richer fundamental group, but not one that's so rich that you have non-trivial SU2 representations?
Yeah, so it doesn't admit. Anyway.
Wouldn't that simply connected doesn't admit a non-trivial not SU2 representation either because it's simply connected?
That's right. Well, go on, but I think you just need to put a does not in between pi 1 and admit. No?
Wait. No, I'm worried.
Well, no, I think you're doing it right. It's just that the wording is not right.
I agree with Daniel.
So admits
Because if you take any sigma, well, at least conjecturally, every sigma connects some sigma bar, unless it's the S3, is supposed to have a non-trivial representation. Or that's what we expect. So that's not much of a hypothesis. It's not that anyway.
wait, but
Go on. I think I don't know if Nikolai agrees. Then I think I'm right. I'm expressing my faith in Nikolai.
Yeah, you shouldn't probably.
I also agree.
Yeah.
It would be pi
I'm
1
worried
not.
did I apply it wrong?
No. I'm sure you did it right. Because morally, what you're
Oh
saying.
yeah, right. Yeah, does not.
I think you
does
just
not
wrote it
admit.
down wrong.
Yeah,
That's
so
all.
yes, so the pi 1. Yeah, I guess you're right. It does not. Sorry, I'm getting a little caught up. It's a little Okay. Yeah. Okay. All right.
Yeah.
Right. Yeah. Okay. We're good. Okay. So where was I? All right. So the point here is this obstruction. So this obstruction, or the modified version that I came up with, isn't actually that hard to satisfy. You can just add a bunch of two handles to kill pi 1, and the thing that you get on the other side would be obstructed from embedding in S4. But the point is you need to kind of thread the needle of both doing that and having something that embeds in a homology S4, right? That's the trick, right? And so to do that, we need good families of homology S4 embeddings, right? All right. So how do we get those families? Okay, so first we're going to start with a definition. So this is where the surface slicing comes in. So let F in S4 be a knotted surface. In this case, it'll just be a sphere. I'm just kind of stating it generally. Then a knot in S3 is the slice of F if the knot is the intersection of F with some equatorial S3. And so, this is roughly the schematic you should have in mind. So, we have the S4 in purple, we have our equatorial S3, and then we have our F, which kind of intersects in this red K, which is our knot. All right. So why do we care about this definition? Well, if F in S4 is a knotted surface and K in S3 is a slice of F, then there's this natural embedding of branch covers, right? So, the n-fold branch cover of S3 branched along K embeds in the n-fold branch cover of S4 branched along F. We'll only care about the double cover, but again, I wanted to state it kind of more generally. And of course, the idea here is, if you have this covering map to S4, then if you look at the pre-image of the equatorial S3, then that'll be, this n-fold cover of S3 branched along the intersection of S3 with F, which of course is K. All right. So yeah, again, and there's this sort of natural embedding of branch covers. All right, so the point here is that if the n-fold branch cover of F is an integer homology S4, then we can find families of embeddings using slices, okay? So, but, that's a nice thing to say sort of in the abstract, like, oh, you just cut the surfaces, but like how do you cut the surfaces? Like literally what knots are you getting and how are you getting those knots? And so that's what we're going to talk about here. So in order to do this, we're going to talk a little bit about broken surface diagrams. So a broken surface diagram is kind of the surface analog of a knot diagram. And so I'm just going to kind of do this side-by-side comparison here. So what really is a knot diagram? A knot diagram, well, it's an our knot is sort of an embedding of S1 and S3, and so, if we think about projecting S3 down to S2 by, maybe removing two balls and just like collapsing along that I factor, then we'll get an immersion of S1 into S2. And then we'll also have this extra crossing information, which tells us at the points of intersection, what sheet is kind of higher versus lower in the knot. So for surfaces, you can do the same thing, right? You have an S2 and S4. Let's just assume it's S2 for this case. You can do it for any genus though. Again, you could project down to S3 in the same way that you would project down to S2 for S3. And then from there, you'll get this broken surface diagram, which is, an immersion of S2 and S3 plus some crossing information. And of course, there's like regularity properties in the same way that, no triple points. There are no triple points in a knot diagram. The triple points are isolated in a broken surface diagram. And you have this nice kind of one-dimensional intersection locus, okay? So furthermore, we're going to want to use what's called a Decker set diagram, which is going to be the kind of surface analog of a chord diagram. So what's a chord diagram? Well, a chord diagram is kind of keeping track of the places that our knot is self-intersecting, or our knot diagram is self-intersecting, excuse me. So really what it is it's a pair of an abstract S1 with marked pairs of points corresponding to self-intersections of the knot diagram, and maybe we'll make the convention that the alpha points are always above the beta points in the projected coordinate. Okay. And I'll show examples coming up. And so what is a Decker set diagram? Well, it's the same idea. So again, it's an abstract, surface, S2 in our case, with marked pairs of curves or arcs corresponding to the self-intersections of the broken surface diagram, like the immersed surface, along with functions identifying the points on each curve. So, we want the functions just to make sure that we know kind of how it's intersecting specifically, like which point gets mapped to which other point in the projection. Of course, in chord diagrams, you don't need that because you're only dealing with pairs of points, but, it's nice to have those functions as well. So that's what the alpha 1, beta 1, F1 is. The F1 is the function. Okay, so why is this perspective useful? Broken surface diagrams are like kind of awful to deal with. Like, you don't want to, it's hard to draw immersed surface diagrams. It's hard to like do anything with them. But the nice thing about these diagrams is that they naturally sit in S3. And so you can draw curves on the broken surface diagram that are knots. And my idea is like, maybe some of those are slices, and maybe you can understand when those are slices. Okay. Does that central point make sense to people? Okay. So this is kind of the first part where I come in. So if we have some separating curve on the Decker set surface F, which is gamma, and then let F1 and F2 be the components of the complement of gamma, then gamma represents a slice if F of alpha intersect F1 is contained in beta intersect F1, or vice versa for F2. So maybe it's not clear what that means right now. It'll be clearer once I get to an example, but let me just explain the rough idea of like the proof here. So the idea is we want to upgrade our broken surface diagram representative, like our immersed surface to a knotted surface, like an embedded knotted surface with gamma as a slice. And so the idea is that we're going to be thinking about this broken surface as living in some equatorial S3, and then we're going to push F1 up, or maybe it's down, but like, push F1 in one direction and push F2 in the other direction. And the idea is that if we can successfully do that, right, if we can push F1 into the, the top ball and push F2 into the bottom ball, then, the only intersection of this, surface with S3 will be gamma. And then, if we can kind of push things up properly, we should be able to actually make it an embedded surface, not just an immersed surface. And in particular, if we're just pushing in the projected coordinate, the corresponding broken surface diagram for this resulting knotted surface will be the broken surface diagram we started with, because we're only changing the projected coordinate. And essentially what this condition guarantees is that F1 and F2 are not going to be bumping into each other as we kind of push them in those various directions. Okay. So you can see like alpha of F1 is contained in beta of F1. That says that like as we push, let's say if alpha is the above curve, then let's say as we push F1 down, we want to make sure that, the things that it's above are never contained in beta. Otherwise we would crash in, or sorry, contained in F2. Otherwise we would kind of crash into F2 as we're trying to push everything down. Okay. Questions about that? Okay. So let's get into some examples. So the only example we'll actually need for this for this project in particular is just going to be spun knots, which are some of the simplest two knots you can come up with. I do have actually a more general theory for more general two knots and more general broken surface diagrams, which I've been working on. I could tell you a little bit more about it at the end if you'd like. Okay, but what are spun knots? So a spun knot is a knot that you can, or a two knot or a knotted surface that you can associate to any given knot. And so let's say if you have a knot, then we're going to associate a tangle to that knot by essentially removing an unknotted tangle from that knot. And so we'll get kind of a ball with all the knotting information of that knot in the ball. Okay. So what spin of K is it's basically the boundary of that tangle cross D, the boundary of that tangle cross D2, which naturally lives in B3 cross, the boundary of B3 cross D2, which of course is S4. The other way you can think about it is rather than doing this boundary of crossing with D2, you can think about it as cross S1, but then you need to kind of crush the boundary fibers. So for anything in the boundary of tangle of TK, you would have to associate, you would have to kind of identify those all together. It's just this kind of boundary operation kind of does that for you. Okay, so we have this example of our knot, and so now what we want to do is think about a projection. So our projection is going to be the following. So rather than kind of think, so what I'm going to do is I'm going to kind of project S4 to S3 by projecting each B3 to B2, because that'll get me from kind of the spin of S3 to the spin of S2, which is S3. So you want to project each B3 to this kind of to some like equatorial B2. And if we think about what's going to be happening on each ball, each ball is going to have a tangle in it. And that means that we're going to be projecting each ball to kind of the knot diagram for that tangle ball. Okay. And so what that tells you is that the broken surface diagram of the spin of K is the spin of the knot diagram, i.e., the associated immersed surface is literally, the knot diagram, the spin of the knot diagram. So the boundary of the diagram cross D2 living in B3 cross D2, or sorry, in B2 cross D2 or D2 cross D2. Okay. Furthermore, the Decker set is going to naturally be the spin of the chord diagram. So let me give an example of that. So, again, they wouldn't necessarily be marked this way with colors, but like, let's say we have a knot. I mean, this is only two crossings, so it's maybe not the most realistic thing, but, this is roughly what I mean. So associated to that knot, we'll have, TK, right? where you can see that the points are in the same order. And then of course we would have the spin of K, which would be something like this, where we get all these kind of concentric circles. If you think about this, right, this is really the boundary of crossing this with D2, right? And then finally, I'm just going to be drawing it this way, like as a map where kind of the horizontal lines are latitude lines and the vertical lines are longitude lines. Okay, it's just kind of easier to draw diagrams that way. You don't really want to draw on like a sphere. I don't know, it's too much. Any questions about this construction so far? Okay. So I guess we can just, give another example where, we have the trefoil. So if we take the trefoil, we take its associated tangle, we take the kind of the chord diagram associated to that. So like, these arrows are pointing towards the undercrossings in this case. And then from there, we'll get a broken surface or a Decker set, a broken surface diagram, yes, but I'll be just dealing with the Decker set. And that looks something like this. And this green curve is going to be a slice of that Decker set, which I've drawn the knot diagram of here. And so you can see that in particular, this is K connects on K bar. Okay. So, the first question you might have is, why is this a slice? Well, let's look at our criterion and look at what's happening at each circle pair. Okay. So let's say this, so let's I guess color this in red. This is maybe F1 or something. And the outside in blue. Okay. And then let's look at each circle pair. So at each circle pair, if we look at the overcrossing, it looks like it's kind of split up like this. And if we look at the undercrossing, it looks like kind of the distribution of red and blue is split up like this. And so the point is that kind of, you can see that like the red is always kind of the smaller portion of red. So the red in the overcrossing is always kind of contained in the image of the red in the undercrossing. And again, the implicit choice that I'm making here is that, okay, so first of all, these circles are mapped to each other by essentially the same identifications that we get from the chord diagram, but also that, if we take a given point, F maps it to, kind of the same longitude point on its corresponding circle. Okay. And so that's why I get kind of this sort of little jigsaw piece, because the idea here is that this is kind of, these kind of back and forths are exactly matching kind of the alternatingness of the trefoil knot. And that's why I get this. And so the point is also that, this always, like this particular kind of circle configuration satisfies our criterion. And because the configuration looks like this for every circle pair, we know that it's a slice. Okay. And of course, we know that this is a slice of the spin of the trefoil. Naturally, I mean, there's kind of this canonical ribbon disk. And, the double of that ribbon disk will be the spin. Okay. But one thing to note is that the double branch cover of this is the double branch cover of K connects some, the mirror of that double branch cover. And also, I guess one thing I should mention is, I guess, the double branch cover of spin of K is equal to, the spin of the double branch cover of K. So if this is a homology 3-sphere, then this becomes a homology 4-sphere, and that'll be important moving forward. Any questions about that? Maybe people don't immediately see why this is a slice, at least according to my criterion, but there is a method to the madness, is I guess all I want to say. Okay. So the key idea.
So
yeah.
I'm one of the people who doesn't see that, but which I don't want to, but is this slice, I know this is simpler probably than your regular, the full construction, but is this slice the same thing that you get by sort of naively just spinning the arc, sort of spinning the arc through?
Well, so if you, the issue is that like that won't be, I think that spinning that won't give you, like that won't be embedded, right? Because the knot diagram isn't embedded.
Like in Arten's, or I guess it's Arten's original description of the spin of a knot, you imagine, sort of, here's this, I don't know, horizontal plane, and then you have something that sort of flies around.
Yeah.
Is that the same slice? Is that the slice that you're?
Well, so again, like if you wanted to draw, like you're talking about like a given level set of that, right?
No, I wasn't really thinking of it in terms of level sets. I was thinking of it in terms of like, I don't know, so like polar coordinates or something. I mean, it's very similar to.
Yeah, well, I think that so it's, we have the, like this spinning of the knot, and like the idea is that, if we wanted to go, okay, so like what is a longitude line in this case? A longitude line is a copy of the, the tangle diagram. It's this, but it's literally this. It's like it's immersed. It's an immersed curve. It's not an embedded curve. Okay, and so the idea is that, these kind of look like longitude lines, but you can see that there's kind of this left and right movement, right? And that left and right movement is exactly giving you the over-unders that give you a copy of the knot.
Well, I'll have to think about it.
Yeah. It's, it's a lot of this talk is like showing you pictures and just like, again, and asking you to believe them, I guess. All right, so other questions? Okay. So the key idea of this criteria is that it actually depends only on F1 intersect alpha and F1 intersect beta, right? So, slicing modifications that preserve F1 intersect alpha and F1 intersect beta will preserve the fact of being a slice, right? So, for example, like if we start with this example here, we can, we see that there's this annulus, right, here. And so we could actually kind of like Dane twist along that annulus, and you can see that the intersection of, if we draw this, if we kind of fill this in, the intersection of it with all of the kind of dotted or solid curves will be exactly the same, and so it'll still be a slice by the same logic as before. Okay, but what's the effect that this has on the knot? Well, it turns out that so there's this kind of canonical ribbon disk for K connects to K bar, and it basically adds a full twist to one of the bands of that canonical ribbon disk. Okay, so how do you see that? Well, there's kind of this natural annulus that I've kind of drawn that lives here. And you can see I've kind of Dane twisted along this, but if you think about like the curve that I've drawn here, it looks a lot like this. If you, do some isotopy. And then the crucial part is that this is the same thing as doing -1 surgery on this black curve here. And that's going to be really important because we want to construct some cobordisms. Okay, so, I guess the first thing that I'll note is that we can kind of full twist any of the canonical bands like this. And of course, we can come up with a broken surface diagram corresponding to any symmetric kind of form for K connects M K bar, i.e. if we take a different different tangle diagram, we'll get a different broken surface diagram, and there'll be different bands that we're allowed to twist. It turns out that, adding these full twists to these bands is exactly the family of knots that corresponds to what are called even symmetric unions. So what is a symmetric union? Well, a symmetric union is something that looks like this. So it's, we have this, connect sum here. But then we also have other symmetric regions, which we add some number of twists to. And even symmetric unions are ones where we only add an even number of half twists. And again, the reason we do that is because this adds a full twist, not a half twist. So the other thing to note is that how do I get this cobordism from, K to these you know, we're going to get an associated cobordism from K to these symmetric unions. So, you know, if we attach just two handles onto, you know, the complement of K cross I, then we'll get this kind of cobordism from the complement of K to the complement of the symmetric union. And then, of course, that's going to naturally, by taking the branch cover, give us a cobordism from the branch cover of K, or sorry, not K, I want to say K cross K bar here. That's going to give us a natural cobordism from the double cover of K cross K bar to the double cover of the symmetric union. So the idea here is that, you know, we start with XK cross I, and then we add these two handles. And then that's going to give us the double branch cover. We're going to get the double branch cover of S3 cross I, union those two handles branched along K cross I. And then, you know, one point to make is that if you look at these curves, this is an even number of copies of meridians, right? It's you know, it's this meridian plus this meridian. So that means that these curves, you know, kind of the attaching regions will lift to two curves rather than one curve. And so we know that this is going to lift to two handles each. And so we're just going to get, you know, some two handles. They're different two handles. It's twice as many, but it's still going to be kind of this branch cover plus some two handles, which gives us, again, this branch cover cross I union some two handles. Okay. So this is our cobordism. Questions about that construction? Okay. Alrighty. So what do we actually need to do? So we have like this construction. We have you know, a manifold, but also a cobordism associated to any even symmetric union of K. And so what do we need to actually verify to show that, you know, to get everything to work out and for me to prove my theorem? So we need to verify that these are going to be definite cobordisms, and we need to verify that, you know, there's some pi1 condition. I haven't really specified exactly what that is. So first, definiteness. So it turns out that this cobordism has a diagonal intersection form, and the diagonal elements are going to be plus or minus ones, and those are going to correspond to the signs of the twists. The idea there is essentially that, you know, I guess one way you can think about it is you can kind of think about everything downstairs, and then the point is that these will all be one framed, and they won't link each other. One way you can see that is by kind of attaching kind of the exterior of the natural disk for K connect some K bar, and you can see that these will all be kind of the attaching circles of these will all be slice in the complement of that disk, right? Because, you know, we can see that they're kind of these like what I call like meridians of bands. Let's see, where do I do that? Yeah, so you can see that it's kind of this natural meridian of a band. So once we kind of get rid of the band, there's kind of nothing obstructing it from just kind of closing up into a disk. And so, you know, we combine that disk with the actual core of the two handle, and we'll get a sphere, and all those spheres will be disjoint and framed, you know, with self-intersection number 1. And so then in the cover, the same thing will be true. We'll have a bunch of spheres, self-intersection 1, disjoint. Or I guess it's plus or minus 1 corresponding to the sign of the twists. Okay. So the second part we need is this pi1 condition, which is that, you know, infinitely many of the cobordisms associated to these even symmetric unions have pi1 equal to just the double branch cover of a single copy of K, not K connects its mirror. So the idea, and it turns out that that's sufficient. So the idea here is you just attach enough two handles to identify a generating set of sigma of the double branch cover with the other part of the double branch cover, because if we think about what each of these kind of two handles is doing to pi1, well, it's going to be identifying, you know, it's going to be identifying this meridian with this meridian, right? In our K, right? And so, you know, we just need to find a generating set of K, or pi1 of K, and if we attach kind of two handles to each of those, then, you know, that'll be sufficient. So in particular, I think I have an example at the bottom. Yeah, here. So here's the example that I have. So, this is T3, this is kind of a double of T3-5, but then I've added these two full twists. And the idea is that this is sufficient because this is kind of one along each bridge for a bridge presentation of T3-5. Of course, there's only two instead of three because this is kind of connects on the mirror because there's like an inherent kind of extra relation added just from doing the sort of amalgamated product there. But it turns out that, with that amalgamated product, these two are sufficient to get the pi1 that I want. Okay. Great. Okay, so now we get to the proof of the kind of main theorem here. Now I'm going to specify what I want K to be and what I want the double cover to be. So K is going to be T3-5, the 3-5 torus knot. And the reason we're choosing that one is because the double cover of that is P, the Poincare homology sphere, which means that the spin of that is going to be the spin of the Poincare sphere, which is a homology force sphere. Okay. Then J is going to be a symmetric union along K such that the associated cobordism W has pi1 of W is equal to, pi1 of the Poincare homology sphere, and W is definite. Okay. So then we want to assume that the double cover of J embeds in Y, which is Y, embeds in a homotopy sphere. Okay. Which we'll call S, and S minus Y has components X1 and X2. Okay. And then we're going to define a few other spaces. I'm not going to say manifolds because one of them is not a manifold. So first of all, we want to define Wi as being just, attaching Xi to W. And then we want to define T as, I wrote T for kind of triad. And the idea here is that we're going to be kind of attaching both X1 and X2 to W. And so we get this kind of non-manifold part, but this is still, it's still a space, right? Okay, so first of all, the first thing I'd like to note is that pi1 of T is equal to 1. So why is that? Well, it's because you can just do it by Seifert-Van Kampen. These two together form a homotopy sphere, and this is just built out of two handles, so it's not going to be adding anything to pi1. It's just adding relations, not generators, so it's still going to be easily connected. Okay. Another thing to note is that T is equal to W1 union W2 glued along W, right? So what we want to do here is by Seifert-Van Kampen, we get, this push out. So pi1 of W goes to pi1 of W1 and W2, but also goes to 1, okay? And so the nice thing here is that, and then I guess the other thing I'll state is that GI is going to be the image of, FI here. So, the image of this map or the image of this map. Okay. And so then the final point here is that pi1 of W, which is pi1 of P, or the Poincare sphere, has a really small fundamental group, and that'll be important. So again, pi1 of P is just SL2 F5, which only has itself A5 and 1 as quotients. So really what we're going to be doing, the last part of this theorem is just going to be a case analysis on GI, which again is the image, which we know has to be a quotient group. Okay. So the first case is that G1 is 1, which that's the easy case, right? Then we know that pi1 of W1 is 1, which means that W1 is the manifold we need for our obstruction, which because it doesn't admit an SE2 representation. Okay, we're good. Great. So the second case is A5. And so this is where the SU2 representation, not just simply connected part, is going to come in. So, so the image of, the boundary, right? Or I don't want to write W1 here. I want to write pi1 of W1 is going to be A5 in that case, right? Because because, pi1 of just W, there's kind of this natural inclusion of pi1 of P into pi1 of W. And that's going to be, all of our SL25. And then we just look at how that SL25 maps into pi1 of W. And that's going to be as this A5. Okay. But the point is that A5 does not admit a non-trivial SU2 representation because it has, you can see that by the classification of spherical manifolds. You can see because A5 is simple and has more than one order 2 element, whereas SU2 only has one order 2 element. But either way, it doesn't admit a non-trivial SU2 representation. And we said that our SU2 representation has to extend non-trivially to the boundary, but it can't extend non-trivially because, of course, the image of our boundary K1 is A5. Okay. And then finally, what's the last case? Well, the last case, I just showed you that not just W1 can't be these first two groups, but W2 also can't be those first two groups. So without loss of generality, G1 and G2 both would have to be SL25. But in this case, we know that not F and G, we want to write F1 and F2. We know that F1 and F2 are injective. And so then we're going to be using this kind of general group theory statement, which is there's this normal form for free amalgamated products. It turns out that if F1 and F2 are injective, then alpha and beta are also injective. Again, alpha and beta are sort of the final two maps here. But those two can't be injective because this is just, the trivial group. And so, that's our kind of final kind of contradiction that finishes off the case analysis. And, here's an example. Or I guess, yeah, that's our example. Okay. But of course, there's infinitely many of these, you can add any, like once I get to here, you can add any number of twists as long as the twists are all of the same sign. Okay. So I guess that's about it. I'll leave some time for questions. So yeah, thanks for having
I'm
me.
sorry, I missed the part about the definiteness of the cobordism. Why is
Oh
it
yeah,
definite?
so again, the definiteness, we're gluing on an integer homology ball, and we showed that the cobordisms are definite.
You had those plus and minus ones though, right?
Right, so the point is that as long as the twists are all of the same sign, the cobordism is definite.
And they are all the same sign.
Yeah, well, you can choose to make them. I mean, they're not
okay.
automatically, but you can choose to make them all the same sign.
So in your example, they are all the same sign.
Yeah, so there's two twists here, and they're the same sign.
No. Okay.
I guess any other questions? I guess yeah, I'll end the talk here.
So presumably you could, if you wanted to, just sort of draw. I mean, obviously you found this by this method, which you've been, as you said, you were kind of sitting on for a while, but is there some sort of, I don't know, I mean, I suppose you could just draw a picture of the homology ball on this homology.
Yeah, you could, I mean, in theory.
but it's not particularly revealing, I guess, is what you're saying.
I don't think so. Maybe it is.
Yeah. Anyway, cool.
Yeah, nice stuff, Clayton.
Yeah. Yeah, I mean, I guess one thing I could mention is like if no one has any questions, I can mention kind of the more general theory here. So, so obviously spun knots are kind of like a simplified case. Like for example, there are no triple points in the Decker sets of spun knots, right? But more generally, you will have triple points, and more generally, you will have quite a few of them. And so the interesting thing is that, like, from the Decker set for a surface, you can kind of naturally get a handle structure on that surface. And so, and depending on kind of how you draw that handle structure and kind of how you draw your slices, you can actually get, a handle structure on each of sort of the disks for your slice. And so the idea here is that you could potentially find counterexamples to the slice ribbon conjecture using this strategy, because not only are you finding kind of, in some sense, random slices of spheres, but you also can kind of pre-screen which slices kind of naturally have ribbon disks, because you kind of see what the handles are. And that's kind of, one of the things that I've kind of been working on with this project. The issue is that, as you get to more complicated broken surface diagrams, the visualizations get harder and harder. And so that's been a bit of a challenge. But I figured, as an advertisement for this perspective in general. I guess that's about it. I mean, yeah. You could do this with more general manifolds, like more general base manifolds, but like you probably need to know a little bit about their SU2 representations. Like this was pretty nice because like SL25 is just really small. But I don't know, if you knew better group theory, maybe you could still run this argument.
Thanks, Clayton. That was great. I have one comment about the reference. Can you go back to Taub's theorem?
Yeah. Maybe did I not cite it properly?
No, it's good.
Where are we? Here.
So you just skipped it, I think.
That's right here.
Oh, the generalization below it.
Oh, the generalization. Okay.
So that there's two things here. One is that the Froschov meridian is non-zero, and then there's the other part of this generalization, which is the part that you use.
Yeah.
But that's already in Taub's original theorem. I just wanted to point that out.
Oh, okay. I guess it's just not how it's stated, which is, I don't know.
I think I just checked his paper. I think that's not stated.
Okay, well, I guess I didn't need all these statements. I just needed Taub's statement. Oops. Doesn't mean I should not cite him.
I don't mean to take credit away from Ali.
Yeah, it is possible you could get some other interesting things using, like without closing it off, which is sort of the point of the H. Sigma not equal to 0. There might be some other sorts of examples that you could cook up.
Yeah, it's just
where you
like,
didn't need to
I'd be wary of trying to do that because, like, again, I just think that the group theory of it will probably be a lot messier.
Well, whatever.
Maybe not. I don't know. Yeah. But yeah, that's a good note. Thanks, Chris.
I have an embarrassing question. I don't know, it's not an embarrassing question. Just, I don't know, if you have a reasonably presented group, can some other any kind of software that can actually just check for representations into, I know if it's like finite groups and stuff you can, but like SU2 or stuff like that.
It's tricky algebra. I mean, people have studied it in special cases, like Riley way back, Eric Klassen's thesis, but to say big cases, so I'm certainly not aware of any software.
I mean, at some level, you're writing. I mean, what Riley did was, which he did for sort of two-bridge knots, is you write down some sort of algebraic curve, and you're looking by looking at traces of things, and you're looking for, sort of to asking another hard question: are there points on this algebraic curve? And so that's a hard problem. like a real algebraic curve to boot. So it's you know, it's pretty difficult.
Sure.
Bye.
Well, we are getting a little bit more organized. In 2 weeks, Ian Zemke will speak, and that's listed. In 4 weeks, Hiyoto Omori will speak. Those are listed on the website. We'll keep updating the website with more information.
I guess.
Yeah. Well, thanks, Clayton. If you send me your notes, I'll put them up on the website with the video, if that's okay.
Sure. Yeah.
All right. Nice.
I mean, yeah. Yeah, it's tough because like it's very like it's tough to figure out extra questions for this because it's like very self-contained and like somehow like most of the generalizations like are probably kind of hard.
Yeah, well, the question's been around for a while with sort of these ideas, but nobody's put it together until now, and you've done a really nice job putting all the pieces together. It's pretty.
Yeah, thanks. Well, one of the inspirations for this was actually using kind of, I guess like one of the inspirations for this like general construction was actually your paper about like like a homology.
Yeah.
Sphere with the knot surgery, that one. But yeah.